Analysis of high-pressure fuel pump failures in modern diesel engines, mechanisms, diagnostics, and corrective methodologies. Introduction to common rail diesel injection and high-pressure dynamics. The evolution of modern diesel engines has been inexorably linked to the continuous advancement of high-pressure common rail injection systems. In the pursuit of stringent emission compliance, enhanced fuel economy, and superior power output, automotive engineers have continuously increased the hydraulic demands placed upon the high-pressure fuel pump. In contemporary diesel power plants, such as the Ford 6.7 liters Power Stroke, the General Motors 6.6 liters LML Duramax, and the 2019-2020 Ram 6.7 liters Cummins, the HPFP is tasked with taking low-pressure fuel from the lift pump and pressurizing it to extreme thresholds, frequently exceeding 26,000 to 29,000 psi. This immense pressure serves a critical thermodynamic purpose. It atomizes the diesel fuel into microscopic droplets upon injection into the combustion chamber, facilitating a more complete, efficient, and cleaner combustion process. However, the architectural design required to generate such extreme pressures within a compact housing pushes the absolute boundaries of mechanical engineering, fluid dynamics, and metallurgical endurance. At the center of this technological paradigm is the Bosch CP4 series injection pump, a component that has garnered a notorious reputation across the global automotive industry for catastrophic, unprovoked failure. The fundamental operational paradox of the modern diesel HPFP is its reliance on the fuel itself for internal lubrication. Unlike the internal combustion engine's rotating assembly, which relies on a pressurized hydrodynamic film of high-viscosity engine oil to separate moving parts, or older systems like the 6 liters Power Stroke's HEWE system that utilized engine oil for actuation. The internal components of the HPCR pump must survive utilizing the inherent lubricity of the diesel fuel passing through its crankcase. This requirement creates a severe vulnerability when the pump is subjected to regional fuel variations, particularly the adoption of ultra-low sulfur diesel in North America. The refining processes required to remove sulfur from diesel fuel, mandated for environmental protection to reduce particulate and sulfur dioxide emissions, fundamentally stripped the fuel of its inherent lubricating properties. Consequently, the tribological environment within the pump degrades. When the fuel's lubricity falls below the threshold required to maintain a microscopic boundary layer between hardened steel components, the pump experiences acute metal-on-metal friction, accelerated component wear, and eventually a systemic mechanical collapse that annihilates the entire fuel system. This report provides an exhaustive, expert-level analysis of the known problems associated with diesel high-pressure fuel pumps failing to make pressure, specifically focusing on the cam and roller desynchronization phenomenon. Furthermore, it delineates the optimal methodologies for remediation and outlines the rigorous procedures required for precise installation and timing. The mechanics of pressure generation and architectural tolerances. To fully comprehend the catastrophic nature of HPFP failures, one must first analyze the transition from legacy fuel systems to modern HPCR platforms. Older rotary-style injection pumps, while less efficient, possessed relatively loose internal tolerances. These legacy pumps could handle minor debris and poor-quality fuel without immediately self-destructing, often utilizing fuel filters rated at a porous 10 microns. The advent of the common rail system necessitated a paradigm shift in manufacturing precision. Modern high-pressure fuel pumps, such as the Bosch CP4, require components to be machined and assembled in environmentally and temperature-controlled clean rooms. The internal operating tolerances of these pumps, and their corresponding piezoelectric or solenoid injectors are frequently as tight as 3 microns. To place this dimension into context, the average human hair measures between 50 and 80 microns in diameter. Therefore, the internal clearances of a modern HPCR system are approximately 20 times smaller than a human hair. Because of this extreme precision, fuel contamination and lack of lubricity become exponential threats. Microscopic contaminants, water, or air bubbles that would easily pass through an older rotary pump act as highly abrasive cutting tools within the tight confines of a CP4. This necessitates the use of absolute micron-rated filtration, as any particle larger than 3 microns can lodge between the plunger and the barrel, score the precision surfaces, or disrupt the seating of the delivery valves, immediately compromising the pump's ability to compress fuel and make pressure. The Bosch CP4 architecture is divided primarily into 2 variants, the CP4-1 and the CP4-2. The CP4-1 utilizes a single pumping element and is typically deployed in smaller displacement, light-duty diesel engines. Conversely, the CP4-2 features 2 pumping elements arranged in a V configuration and is the standard fitment for heavy-duty V8 and inline-6 applications, such as the Duramax, Powerstroke, and Cummins. While the output volume differs, the fundamental internal kinematics and the fatal flaws inherent to those kinematics remain identical across both variants. The root cause, cam and roller desynchronization. The primary mechanism of failure within the CP4, universally recognized as the cam problem, is the catastrophic desynchronization and subsequent physical destruction of the cam and roller tappet assembly. A forensic examination of the pump's internal kinematics reveals why this failure occurs with alarming frequency. Inside the CP4 pump casing, a gear-driven central camshaft actuates the high-pressure plungers. In the CP4-2 configuration, the shaft features a 2-lobe cam that drives the 2 diametrically opposed plungers, resulting in 4 distinct pumping pulses per revolution. The physical interaction between the rapidly spinning cam lobes and the linear plungers is mediated by a roller tappet assembly. In a perfectly functioning, idealized fluid environment, the roller rides smoothly along the hardened steel cam lobe, translating rotational motion into the linear actuation required for the plunger to compress the diesel fuel. This critical relationship relies entirely on an unbroken microscopic layer of diesel fuel being present between the roller and the cam at all times. When ULSD is introduced into this high-stress environment, the fluid film thickness is often insufficient to prevent microscopic asperity contact between the metals. The fatal architectural oversight of the CP4 design is the absence of a mechanical keyway, guide pin, or positive locking mechanism to prevent the roller tappet from rotating within its bore. The alignment of the roller parallel to the cam lobe is maintained purely by the hydraulic pressure of the fuel above it and the continuous spring tension against the cam lobe below it. When the pump experiences fuel starvation, or when highly aerated fuel enters the piston chamber due to a weak lift pump or a clogged fuel filter, the hydraulic pressure stabilizing the tappet is momentarily lost. The piston assembly is essentially allowed to float. During this microscopic window of zero tension, the severe operational vibrations of the diesel engine, combined with the extreme friction caused by poor fuel lubricity, can cause the lifter to spin 90 degrees within its bore. Once the roller is turned sideways, resting perpendicular to the cam lobe rather than parallel, it ceases to roll. Instead, the hardened steel edge of the sideways roller acts as a stationary chisel or pile driver against the rapidly spinning cam lobe. The localized friction generated by this metal-on-metal impact creates immense heat, and the hardened steel components begin to literally machine each other apart. The cam lobes are ground flat, and the roller is pulverized. Systemic contamination and the ripple effect. The failure of the cam and roller does not remain an isolated mechanical event within the pump housing. In the CP4 architecture, the fluid routing is designed such that the fuel responsible for lubricating the pump crankcase is the very same fuel that is subsequently drawn up into the high-pressure pumping elements. Consequently, as soon as the sideways roller and the cam begin shedding metallic shavings, this highly contaminated shrapnel-laced fuel is drawn into the plungers, pressurized to 26,000 psi, and discharged violently out of the high-pressure outlet. The metallic debris, commonly referred to in the industry as swarf, is distributed uniformly throughout the entire high-pressure fuel system. This swarf acts as a highly abrasive slurry. It travels through the high-pressure lines, permanently scoring the internal tolerances of the common rails, and proceeds directly into the fuel injectors. The microscopic pintles and nozzles of the piezoelectric or solenoid fuel injectors are instantly destroyed by the metal particles. Furthermore, because common rail systems continuously return excess fuel to the tank to manage pressure and temperature, the debris flows through the return lines, contaminating the fuel cooler, the fuel tank, and the low-pressure lift pump. The ultimate result is a total system loss. A mechanical failure that initiates at a single point of friction cascades into a catastrophic contamination event, requiring the replacement of nearly every fuel-wetted component in the vehicle, frequently culminating in repair bills ranging from $8,000 to $15,000, depending on the platform and labor rates. Symptomatology and diagnostic signatures of failure. Because the internal clearances within the HPFP and the fuel injectors are exceptionally tight, the transition from a functioning state to a catastrophic failed state is usually sudden. A CP4 rarely provides extensive warning signs before it self-destructs. A vehicle may operate flawlessly one moment and suffer a complete engine stall the next. However, meticulous diagnostic observation can identify the acoustic, electronic, and physical signatures of a compromised system. The primary operational symptom of a failing high-pressure pump is its inability to make and maintain commanded fuel pressure. When the cam lobes are worn down, the plungers cannot achieve their full stroke, leading to a drastic reduction in fuel volume and pressure. This manifests physically as an engine misfire, severe hesitation during acceleration, a rough and shaking idle, or a complete loss of power under heavy load conditions, such as towing or climbing steep inclines. The engine may experience prolonged cranking times before starting, particularly in cold weather, when the engine requires maximum fuel atomization to ignite the diesel charge. The engine control module continuously monitors the fuel rail pressure via dedicated sensors. When the internal pump components degrade and the actual rail pressure deviates significantly from the commanded pressure map, the ECM will trigger the check engine light and store diagnostic trouble codes. The most ubiquitous trouble code associated with CP4 failure is P087, fuel rail system pressure, too low. Additional diagnostic codes may include P0191 or P2291. Acoustically, a failing CP4 may emit a rhythmic, metallic ticking, rattling, or whining noise radiating from the front engine bay, indicative of the hardened steel roller grinding against the cam lobe. Excessive exhaust smoke may also be present. Black smoke suggests erratic overfueling due to damaged injector nozzles, while white smoke indicates unburned fuel from insufficient atomization pressure. If a CP4 failure is suspected based on these operational and electronic symptoms, the most definitive diagnostic procedure is a physical inspection of the fuel control actuator. The FCA, also referred to as the inlet metering valve or MPROP, is an electronic solenoid mounted directly on the exterior of the CP4 pump body. Its function is to regulate the volume of low-pressure fuel entering the high-pressure pumping elements. By removing the FCA, typically secured by two small T25 torque screws, a technician can extract the valve and inspect the fine microscreen located at its tip. If the pump's crankcase has begun to shed metal, the return flow dynamics will deposit this debris directly onto the FCA screen. If the technician observes that the screen is coated with metallic flakes, magnetic swarf, or a fine glitter-like paste, the pump has suffered definitive internal cam failure. Finding metal on the FCA screen immediately confirms the necessity of a comprehensive, system-wide fuel system replacement, as the contamination has already breached the high-pressure chambers. Strategic remediation. Determining the best way to fix when confronting a CP4 high-pressure fuel pump known to possess inherent architectural flaws. Simply replacing a failed unit with another identical OM-CP4 is widely considered by industry experts to be a temporary reprieve rather than a permanent cure. The fundamental design remains highly sensitive to poor fuel lubricity, leaving the vehicle susceptible to repeat failure. To achieve long-term reliability and protect the vehicle from future catastrophic repair bills, the diesel aftermarket industry has developed several distinct mitigation paradigms. Determining the best way to fix the vehicle depends entirely on the operator's budget, the vehicle's specific platform, and the desired level of fail-safe security. Remedy 1. OM pump replacement coupled with disaster prevention bypass kits. For vehicle owners who opt to retain the factory CP4 architecture, either due to strict emission compliance laws, factory warranty constraints, or budget limitations preventing a full conversion, the absolute minimum preventive measure required is the installation of a disaster prevention kit, also known as a bypass kit. The factory CP4 configuration internally routes the fuel used to lubricate the crankcase directly up into the high-pressure pumping chambers. A bypass kit fundamentally alters this internal fluid routing. It caps the internal pathway and reroutes the fuel exiting the pump's crankcase externally, directing it either back to the fuel tank or through a secondary, ultra-fine filtration matrix, rather than allowing it to proceed into the high-pressure elements. If the CP4's roller subsequently rotates and the cam begins to shred, the metallic debris generated in the crankcase is immediately swept out of the pump via the new external return line and safely trapped by the filters. While the high-pressure fuel pump itself will still inevitably destroy itself and the engine will stall, the bypass kit acts as an impenetrable quarantine mechanism. It physically prevents the swarf from entering the high-pressure fuel rails, the injector lines, and the delicate fuel injectors. This containment strategy dramatically reduces the financial liability of a failure, shrinking the cost from a $10,000 comprehensive system overhaul to a localized $2,500 pump replacement. Remedy 2. The S-Stanodyne DCR pump conversion, the most technologically advanced, best way to fix the CP4 problem in contemporary applications, particularly the 2011 present Ford 6.7 liters Power Stroke, is the installation of the DCR pump. Co-developed by SNS Diesel Motorsport and Pure Power Technologies, the DCR is engineered from the ground up to provide true OE fit and function while entirely eliminating the specific vulnerabilities of the CP4. The DCR pump operates utilizing a patented eccentric drive pumping technology that differs fundamentally from the Bosch design. Instead of relying on a fast-spinning cam lobe interacting with a floating roller tappet, the DCR employs a solid floating eccentric ring. Two internal plungers, specially coated in diamond-like carbon for extreme friction resistance and surface hardness, ride directly on the exterior of this floating ring. Because the ring floats and merely articulates rather than rapidly spinning against the plungers. The kinematic motion is exceptionally smooth. This entirely circumvents the metal-on-metal impact points that cause the CP4's roller to shatter. Crucially, the internal fluid dynamics of the DCR are inherently fail-safe. Its architecture separates the lubrication circuit from the high-pressure circuit. It feeds the pump crankcase and the high-pressure pumping elements independently. Even in the statistically improbable event of internal wear within the DCR, the resulting debris is automatically purged via the return line rather than being injected into the high-pressure rails, ensuring the injectors remain permanently uncontaminated. From a performance standpoint, the DCR provides a massive 1250 M&M3/revolution fuel displacement, representing a 25% volumetric increase over the factory CP42. It utilizes a pressure-lubricated cam and robust internal bushings, features a highly corrosion-resistant inlet metering valve, and is fully compatible with low lubricity ULSD and heavy biofuel blends that would otherwise destroy a CP4. Furthermore, the DCR is a true plug-and-play solution. It requires no custom ECU calibration, is fully CARB-compliant, and actively restores low-end torque and throttle response by providing a much more stable hydraulic pressure curve to the injectors. Remedy 3. The Bosch CP3 retrofit conversion. For over a decade prior to the widespread availability of the DCR, the undisputed gold standard for permanently eliminating CP4 anxiety was the CP3 conversion. The Bosch CP3 is the direct predecessor to the CP4, famously utilized in the legendary early 5.9 liters and 6.7 liters Cummins engines, as well as pre-2011 Duramax platforms. The CP3 utilizes an entirely different internal architecture focused on heavy-duty longevity. It features 3 separate pumping elements instead of 2, and similar to the DCR, it utilizes an eccentric drive mechanism rather than the fragile roller tappet design. The CP3's robust construction, larger internal surface areas, and superior fluid dynamics allow it to easily tolerate the lower lubricity of modern ULSD without sustaining catastrophic internal damage. Furthermore, the CP3 architecture supports massive fuel flow rates, making it the universally preferred choice for high horsepower, highly modified engines utilizing larger aftermarket injectors and compound turbochargers. Recognizing the failure rate of the CP4, aftermarket engineering firms developed comprehensive billet aluminum conversion kits allowing the CP3 to be mounted onto modern platforms originally designed for the CP4, such as the 2011 to 2016 LML Duramax and the 2019 to 2020 Ram 6.7 liters Cummins. The severity of the CP4 problem in the Ram platforms was so profound that it resulted in a massive OM recall. NHTSA Campaign Number 21 V880, Recall Y78. Under this recall, Stellantis officially conceded the pump's design flaw and mandated the removal of the CP4 from over 222,000 trucks, replacing them retroactively with the older, more reliable CP3 pump free of charge. While historically highly reliable, early CP3 conversions often required custom ECM tuning to scale the fuel pressure maps correctly. However, modern engineering has evolved, and many current 50-state emissions-compliant CP3 retrofit kits now offer completely no-tune, plug-and-play operation for stock vehicles. Feature comparison of high-pressure fuel pumps.